Okay, let me get the PowerPoints open. Oh wait, that's not how I want to do it. I need to do it from share screen. Okay, and I need chapter 12 open now. And I don't know where the other PowerPoint is, but we won't need it until we get there. Okay, so let me drag this down to the bottom. Okay, and let's see if I can find the current slide we're on with this one. I believe we're at the beginning of density, so that will be okay. Wow, I think, no, that's right. Okay, this was the last slide we had, and that's WAPAC. Okay, so let me go on, and I've got a new toy. At a department meeting not long ago, a week or so ago, an instructor said she was going to send me some information on a Wacom tablet that I could write on, because my old computer died and that's what I used to write on before. I've been having to write with my finger on the whiteboard, and that wasn't all that good. And she sent me this, well, sent me the information. My wife ordered it. It came in late last week. We got it set up this week, over the weekend, so I'm using it now. So that's what I'll try to use this for. Let me, still just 3 of us here, so let's go with the whiteboard. And why it's not starting, I'm not sure. Come on. Okay, there we go. All right, now let me get this taskbar out of the way as much as I can. I'm going to get Jalen out of the way. He's always in the way, you know. Okay. And I'm going to move the whiteboard as far as I can to give me the maximum available writing space. Okay. Now, if you will repeat again what page number we're talking about. 325, got it. And which problem? Number 11 and 15. Okay. All right. So let's start with, well, since they're both on page 325, okay. I'm going to get down my new toy. Okay. Let me see if I can see the pen. There it is. Okay. So this is page 325. See, this is a little bit better than my finger. This is 12.2, problem set 12.2. And number 11 was the first one you said, right? Okay. Now, I'm going to get the book over here in my lap so I can read it better. A 12,000 Newton load is hanging from a steel cable that is 10 meters long and 16 millimeters in diameter. Find the stress. Okay, so what we have here, that 12,000 Newton load, that is a force. Okay, so we'll write that as a force. That's the force due to weight, and that is equal to 12,000 newtons. And that 0 is significant. Okay, that's your force. Okay, hanging from a steel cable that is 10 meters long. Okay, so the length of the cable, and I think they use L for that, but if not, we'll go back and change it. The length of the cable is 12.0 meters if my memory's right. No, 10.0 meters. Okay, 10.0 .0 slash some zeros but not others, okay, meters long. Okay, and 16 millimeters in diameter. So this is the diameter of the cable. That is 16.0 millimeters. Now we have a problem there, don't we, Houston? Okay, it says find the stress, and I think they use S to represent stress, but let me turn back just to make sure. And they ask for what is the stress on the cable. Now, yep, that's what they use. Okay, so stress is what we're looking for. That's supposed to be a regular S. This is the unknown here. Okay, now stress is usually given in terms of square meters, not square millimeters. So what we've got to do, we've got a little bit of work to do first, especially on this, the diameter here. So the first thing we're going to do is get that in terms of meters. Well, a millimeter is a thousandth of a meter, so this would be 16.0 times 10 to the minus 3 meters, because that is what a millimeter is, a thousandth of a meter. So we've just changed it. I didn't use a conversion factor because I knew that one. Did you know it, or do you need me to do that as a conversion factor? Is that okay? Okay. Wait, here's Mercy coming in. Mercy me. What's that? Okay. Now, yeah. Okay. Now, what stress is, just let Mercy in, but I forgot to mark her present. Let me mark her present. And my pen just every time refuses to write. There it goes. So I should have Mercy in now. Okay. Now, what is stress? Okay, stress is from the book, and this is on page 316 in one place. I think it's probably in others as well. Force per unit area. Okay, I can't get it to write. Okay, here we go. Force per unit area. But you know, we got the force up here. There it is. We don't have an area yet. What is area? Of a wire, and we're going to assume it's circular area. Okay, most wires are circular, right? So what's the area of a circle? So here's something we've got to do first, is come up with what area is. Anyone know what the formula for the area of a circle is? You know it, I bet. Now, if you don't know it, what I'm going to do is trying to find to see if they have it in the front of the book or the back of the book or somewhere. I don't see it in the front, so let me try in the back. Okay, here we go. The area of a circle. If you go to the back inside cover of the book, that's what it looks, well, my hand's covering it. All right, I'm trying to hold too many pages in place, and this is flopping on me. So let me do it this way. Let's see if that will work. Okay, back inside cover of the book. See, there's a hard cover, if you got a hard cover. There is the area of a circle. Okay, circle, the area, no, is that a sphere or a circle? That's a sphere. Oh, here we go, I'm sorry. There we go. Area of a circle is, you see it? Pi r squared, right? And I just lost my place, okay, all that, and I just lost it anyway. well, I can find it easily. Got it. Okay, so area is pi r squared. Okay, I'm so used to writing with my finger, I started trying to do that on the screen. So this is pi r squared. Now, tell me right now, do you prefer my stylus on this new device, or do you want me writing with my finger? What do you see better? Is this better or worse? Huh? What do you say? You can see the writing better? Good. Okay. So is pi r squared is the area of your wire. We don't have r either, though. And how is r related to diameter? Exactly. R is 1/2. That's supposed to be an equal sign. This pen has trouble writing equal sign for some reason. It's d over 2. Okay, and now there's a thing up there. I don't have any idea what it is. And it says press Alt to show and hide meeting controls. I have no idea what that means. It's a new device. I don't know it yet. So 1/2 of 16 times 10 to the minus third meters would be 8.00 to get our 3 significant digits in there. 8.00 times 10 to the minus 3. It doesn't do minus signs well either. I'm left-handed and I tend to push. You're seeing several things that are frustrating about this right now. Okay, one is, I don't know. Okay, I don't know what that was doing, but I needed to get out of it. Okay, going back to my draw here. Okay, that is supposed to be a -3, and I never could get the minus sign to right. There it is. That's an ugly minus sign, and this will be meters. That's the radius. Okay, now we've got enough to enter our area formula. Is pi times the radius 8.00 times 10 to the minus 3 meters squared. Okay, now I'm going to have to pull up my handy dandy little phone here that has a calculator on it, get it logged in and all that kind of stuff. Go to the calculator, and don't need to turn it sideways because I'm doing some more scientific calculations. They have the pi key. I don't know if your phone has it, but it's right there near the bottom, right above my finger there. That's the pi key in my calculator anyway. So that's pi times 8.00, or just 8, EE, because this is scientific notation. Then the -3, I have to enter the 3 first, and then the plus minus to change sides. Okay, but then, boo hiss, I'm going to have to start over. Okay, start over. Okay, now here's what I have to do. First, I'm going to enter the pi key times. Now, in this calculator, I've got to open parentheses because this has to be squared, and if I had squared it where it said before, it would have squared the -3. So I have to put this under parentheses, so then that's all I square it. So it's pi times, and then my parentheses key is right up here, right there. You see, there's the open parentheses. So times, I hope it took, well, there we go. Open parentheses, 8 EE 3 plus minus, close parentheses, squared. All right, that's a equal. Okay, that gave me something on the order of 0.000200109 blah 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 blah. There's the answer I got. Okay, that's the area. Now what I'm going to do is write it in scientific notation, and that would be, because that's so much easier to write than this, 2.01, sorry about that, I misread it, 01. I'm going to just round that next one off to a 1. Now I know I've got more significant digits than necessary, but I want to hang on to an extra one there. Okay, and then that's times 10 to the, and now here's what I do is I count the number of places I'm moving my decimal point. There's 1, 2, 3 for the 3 zeros, and then one more for the 2, so it's 10 to the minus 4. So it's 10 to the minus 4, and the units are square meters. Okay, so that's my area. Now I'm ready to enter the stress formula. That's what we're looking for, and we're finally here. So it's 12,000 newtons. Well, some zeros slash and some don't. 12,000 newtons divided by 2.011 times 10 to the minus 4 meters squared. Okay, now I'm going to do a shortcut here. You don't have to do that. You can pull back out and punch in those numbers. Since I've got the denominator there, I'm going to do a 1 over x key. You don't have to do it this way. 1 over x, and then multiply that by your 12,000 newtons. And hit equal, and let Mika back into the classroom. Well, I can't do it on my Wacom. Sorry about this. There. So Mika is coming in, and I can't put her in the roll book with my Wacom pen either. It's an ionizing pen. Okay. I don't know if Mika's in yet, and now my pen won't write at all. Okay, I think I hear Mika. So that pen's no good. It came from Montgomery, no wonder it's no good. So, oh, did I say that out loud? Okay, so that gives us 5 students here. Yeah, 6 participants, I'm one of them. Okay, so when I divided, okay, now I've got to get this out of my lap back onto the computer keyboard gently. When I did that, I got an answer of, whoa, pretty big number. Okay, 5 point, now since this is my final answer, I will round it correctly, 5.97. It was a 6, but the number to the right of 7 is a 6 is a 7, so that rounds it up to there, times 10 to the positive 367, 10 to the 7th, and the unit here is newtons per square meter. That has its own name, and that's a Pascal. Okay, now that's a terribly large number. Okay, now so what we might want to do is write that in terms of kilopascals. And what that would do for us, I'm going to write this down here, that would be same number, 5.97 times 10, and a kilo means 1,000, so I would take 3 away from that and make it 10 to the 4th kilopascals. Okay, or I could take it another 3 and make it 5.97. That's supposed to be a 7. That's pretty ugly, isn't it? Times 10 to the, subtract another 3 from that, and you get 10 to the 1st megapascals. And since that's sort of ridiculous to write it that way, I'm just going to write it as 59.4 megapascals. I don't know if the book does that or not, but those are a variety of answers, all of which are perfectly correct, I hope. Did you check in the back of the book to see what the answer was? This is... Say that again. 59 point... Well, that is a 7. I just can't read my writing. Yeah, I'm sorry. You see, that was such an ugly 7, I thought it was a 4. So let me come up here and get my eraser. Okay, and that is a 7. It's not a 4. Okay. Whoa, what in the world is that? I can't get my draw pen up here to go to the right place. I don't know what's wrong with it. It's stuck. Okay, I swear. Okay. Now I have to, there we go. Okay. This is a 7. Not whatever that worm is. I don't know if I can erase the worm without erasing everything, but let me try. No. This is what's so aggravating about this. I don't know why it does it, but when I go to too much erased, but at least erased the part I wanted to. So make that a 7. Here comes Manasseh. Okay, let me see if I can admit her here. I did. Okay, I can use my iPad or the Wacom to admit her. So here's Manasseh. All right. Now we've got 6 of our 7 faithful attendees, only missing Devin right now. The others we haven't seen from the beginning. So you said that's what they had. I'm sorry? Times 10, oh, right up here. Wait, let me, right up here. Is this it? This line right here? Can you see my pencil? Is that the one you're looking at? I can't hear you anymore. Can you hear me? Your microphone's off. Is that it right there? Yes, sir. Okay. So in other words, your question is how you go from millimeters to meters. Is that right? Okay. So let's do that the other way. Okay. So they gave us 16. You just like my train track method, don't you? 16.0 millimeters. That's what they gave us. Okay. And we're going to try to convert that to a blank, using a blank to equal to a blank meters. Okay. There's our typical conversion method, right? Now, always put the units in their place. Here is the line for the units. One of these units goes on top, one goes on the bottom. Millimeters one place, meters the other. You tell me what goes where. No, you want meters on top. So you put meters on top and put millimeters on the bottom, because you see you want the millimeters to cancel out, leaving you only meters up top, right? You see it? This is a multiplication right over here, and you want that multiplication to be able to cancel things out, including the units. Now I can't get my pen to move. There it goes. All right, now the question is what numbers do we put with the units? how many meters in a millimeter or how many millimeters in a meter? Do you know? Okay, here's sort of a little hint. A meter is the distance from one ear to the opposite finger held out, and I can't show you this. If you can imagine extending out there, that's a meter. A millimeter is the thickness of a dime. So how many millimeters would you think it takes to make a full meter? You said something. It may have been the right answer. Did I hear you say 1,000? Say yes. Yes? Yes, sir. All right, good. That would be 1,000 millimeters makes 1 meter. Okay? Milli means 1,000ths. So that's why it's on the bottom, 1,000ths of a meter. 1,000 millimeters is in 1 meter, just like 1,000 meters is in 1 kilometer or kilometer. The millis and the kilos mean 1,000. Millis are the smaller, kilos are the bigger. Okay? Now, when you divide by 1,000, here's 2 ways you can do it. What 1 over 1,000 means is 10 to the minus 3, because you see if you move your decimal 3 places over, that's 10 to the minus 3. Or you could have divided here and moved this decimal. If I can get my pen to pick up, move it 1 place, 2 place, 3 places. That would also be, so that would have been 0.0160 meters. Now I have to put that last 0 because these 2 are not significant. That one is, and that was a significant digit. So that's several ways to write it. Either 16, like I started to do here, 16 times, or 16.0 times 10 to the minus 3. That's what we did up here. That would be one expression of it. Or you could have written it as 0.0160 meters that way. And you see what you do if you move your decimal 3 places to the right, 1, 2, 3, that makes it 10 to the minus 3 meters. Okay? Because this is a smaller number than 1, so your decimal will be a minus. Your exponent will be a minus. Did that muddy the water, or did it make it any clearer? Okay. All right. And that is the answer they had in the back, 59.7 megapascals? Oh, excellent. I didn't know they would do that. Okay. Now, did you need another one done, you said? It was what? 15. Okay, can I erase this one? Yes, sir, you can. Okay, anyone else need it any longer? Okay, got to find my... Okay, I'll clear the drawings, and it'll be same pages, same section, same everything, except it's number 15. Is that right? Okay, now we have a bar weighing 26.0 newtons supported horizontally on each end by 2 hanging springs. So they're hanging up here holding this horizontal bar. Okay, each of the hanging springs are 15 centimeters long with spring constants of 0.97 newtons per centimeter and 1.45 newtons per centimeter respectively. The bar is 6 meters long and has a center of mass of 2.00 meters from the spring with a constant of 7.970 newtons per centimeter. This is on page 325, number 15, but we're not going to be here long, okay? Because this is going to require you to have something that was covered in a chapter we did not do. Now I can show you how to do it, but it's not going to be useful to you. You will not have one like this on the test, so don't sweat it. But if you do want to see it done, I will go on and do it. The only trouble is, okay, yeah, that, glad you ran into that. I had not read that question before. I didn't realize it was dealing with center of mass, and we don't, center of mass was covered in another chapter well before this one. Okay. Any other questions? All right, glad to. Any other questions, issues, concerns? All right. Where we left off last time, we had finished 12.4 and we're starting 12.5. Okay. And the topic of 12.5, I think I'm going to erase. Well, I keep trying to do it with my finger. I forget I have a new pen. Okay, let's clear that. Okay. 12.5. Density is a property of all three phases of matter. Now the book uses states, I prefer phases. You can have solids with given densities, liquids with given densities, even gases have densities, usually very low densities, but still they have density. And there are two types of densities. One that is used primarily in the SI system, and that's mass density. Okay, so that is called D sub m. Oops, I'm trying to write on the screen. Okay, that's D sub m. That stands for mass density. And as you might guess then, the mass density is the mass per unit volume. Okay, that's a capital V for volume. Okay, now why would we use that predominantly in the SI system? Because we use masses all the time in the SI system. Grams, kilograms, whatever. Do we use masses much in the U.S. customary? Hardly ever. This book's the only place you'll ever find almost them used. And those are measured in slugs. No one measures mass density in the U.S. customary system. They always use weight density. So what is weight density? Weight density is, I'll write it over here, D sub W, that means weight density, and that is not mass per unit volume, but weight per unit volume. Again, a capital V, okay? Only they say their weight, I'm sorry, I'm used to most textbooks just call it W. This is F sub W, because weight is a force. Okay. Now, you could talk about weight density in the SI system. If you did, they would be in newtons per cubic meter. Most of the time we don't do that. We use mass density, which is in kilograms per cubic meter. Okay? I'm trying to get my pen to show up. There it is. Okay? And it's usually only in the U.S. customary system that we use weight density, and that would be pounds per cubic foot. Sometimes other density units, but usually pounds per cubic feet. Okay? So the volume is the volume. Okay. Now, although mass density and weight density can be expressed in both metric and U.S. system, mass density is usually given in the metric system, kilograms per cubic meter. Mass in kilograms, cubic meter is your volume, and weight density is usually in U.S. units, pounds per cubic feet, what I just said. Now, here's a number to know, to trust, and to rely on. Okay? The mass density of water, I'm trying to write on the screen. Okay? The mass density of water, H2O, that's supposed to be an H, okay, is 1,000 kilograms per cubic meter. Now that sounds like a lot, and indeed it is. And by the way, they specify that only that middle zero is significant. Well, the first one is too. The 1, 0, 0, those first three are significant. The last zero is not. Okay? Now, do you have an idea of how big a cubic meter is? Okay? Now, you can't quite see it well, but I'm going to try to lower this. Oh boy, you can't see it well, can you? Okay, I'm going to twist it. Oh, there you see. There's a doorknob on that door. Okay, you can't see it very well, but it's right there on the door. Okay, and that's about 1 meter off the floor. Okay, most doorknobs, look at any doorknob in your house, unless you have some specifically done for kids or say people in wheelchairs and that kind of stuff, usually a doorknob is real close to 1 meter from the floor. Now that door that you see there, that's a closet door, that's about the same width as it is distance from the floor. So that's about a meter. I'm guessing that's about a 36-inch door. That's really close to a meter. So that would be 1 square meter. From the doorknob all the way across down to the floor, that's a square meter. Now picture coming out from the door another meter, which would be more than 3 feet. That would be a huge cube that you've just described. Do you know how much 1,000 kilograms of water is? That is very close to what they call and in fact it is exactly a metric ton. And a metric ton is just a little bit more massive than a U.S. customary ton. That U.S. ton is 2,000 pounds. A metric ton is 2,200 pounds. So that would be more than a ton of water that would be in that cubic meter. So no wonder it has such a high density. 1,000 kilograms per cubic meter, because that would weigh 1 metric ton. Okay, enough of that. Okay, now a cubic meter of water has a mass of 1,000 kilograms or 1 metric ton. The weight density of water, that's D sub W over here, the weight density of water would be, and why that's equal signs just don't draw well here, 62.4 pounds per cubic feet. Sorry, that looks so ugly. Pounds per cubic feet. That is a cubic foot of water. Now, a cubic foot of water is way, way smaller than a cubic meter. Okay? So a cubic foot, if you can picture about the length of your foot, okay, and about the width of your foot, and about the depth of your foot, that's a cubic foot. 62.4 pounds. That's about right. That would be, I think, a fair amount larger than a gallon, but on the same neighborhood of a gallon. Okay, so that's what the weight density of water is. Okay, now in nearly all forms of matter, the density usually decreases with temperature. If the temperature goes down, a solid is going to shrink just a little, not much, but just a little. A liquid is usually going to shrink as the temperature goes down. A gas is certainly going to shrink as the temperature goes down. So in most materials, the density goes down with decreasing temperature. Okay? The one big exception to that would be water. Now, water does get a little bit smaller as you drop the temperature, so from say 100 degrees Celsius down to about 4 degrees Celsius. The volume will decrease a little bit, but at 4 degrees Celsius it starts expanding again. Okay, now the reason for that is water molecules have this very, very, very strong attraction. If you remember, the positive side on the hydrogen ends, the negative sides on the oxygen end, and those molecules stay really close to one end or another of this adjacent molecule. But when it gets cold enough to start making ice, then the crystal structure of ice is bigger than the close proximity of water. So it actually expands from 4 degrees Celsius up to 0 degrees Celsius. It actually is expanding as it starts to form the ice crystal, and by the time it makes ice, it's considerably less dense than water. It's the one and almost only material known to man, naturally occurring on the planet, that actually expands for a portion of its cooling. Okay. Now, they are going to talk about it in section 14.7. We're not doing 14.7. Okay. Now, what I'm going to do now is okay. I'm going to go down here and do the new share, go back to the PowerPoint, Chapter 12 PowerPoint. Okay. And we're going to this slide here, and we'll go from current slide. The last slide in the section, and here it is. Well, it just went. Let me back up one. Okay, there it is. All right. Sorry about this, but this block down here is probably blocking you, but we'll talk about what's there. Okay? Okay, up here we have some of the solids. Aluminum. Now these mass densities in kilograms per cubic meter, those are huge volumes, so those are huge masses. That's 2.7 metric tons. Brass, 8.7 metric tons. Concrete, 2.3 metric tons. I mean, a lot of mass. The unit I'm used to using, but they don't do that in the book very much, is grams per cubic centimeter. A cubic centimeter is like the width of your little fingernail by the depth of your little fingernail by the height of your little fingernail. That would be like a real small cube of sugar, really small cube of sugar, about the width of your little fingernail. Okay, and that would be so many grams. So what you do is just move your decimal, believe it or not, only 3 places, and that's much more usable numbers. 2.7, 8.7, 2.3, 8.89, whatever. Okay, now the weight density, these are sort of big numbers, but not nearly as big as those. These are the weight in pounds per cubic feet. And metals you expect to be pretty heavy. So these solids, aluminum, brass, concrete's a little less dense than aluminum, copper, okay, I'd say cork isn't. Copper is a little denser than brass. Okay, cork is less dense, considerably less dense than any of the others. Ice is 917, where water was 1000, remember? So you see, ice is considerably less dense than water. Iron up there near brass, but not quite as high, 7.8. And lead, really, really dense, 11.3. These are, I go in grams per cubic centimeter. Wood is not as light as cork, but it's considerably lighter than ice. So that's why most wood floats. Okay? And you see the same thing over here. Okay? Remembering water is 62.4 pounds per cubic feet. So you see ice floats, cork floats, and certainly wood floats. Now, liquids. These liquids are alcohol, slightly denser than water. Gasoline, well, I'm sorry, less dense than water. It's 1,000 is water. I was looking at the wrong table. 1,000. So alcohol is less dense than water. Gasoline even less. Mercury, though, oh my goodness, look at mercury. And that's a liquid at normal temperatures and pressure. 13,600 kilograms per cubic meter. That's more than 13.5 metric tons in a cubic meter. Look at this. Even lead will float in water. It doesn't float very much, but it floats some. Okay, that's what density tells you. Who winds up on top if you have a contest there. Okay, Oil is considerably less dense than water, not as low as alcohol or gasoline, but it's still less dense than water. That's why oil sheen will float on the surface of water, unfortunately. Okay. Seawater is slightly denser than water. Water is 1,000, seawater 1,025 kilograms per cubic meter. Or seawater is 64 pounds per cubic foot, whereas regular water is 62.4 pounds per cubic foot. Ice, by the way, remember, was 57. So just a little bit less dense than water. Excuse me a moment. I've been going at it since 8 o'clock this morning. I'm running out of steam and running out of blood sugar, I think. Sorry. Okay. Now these gases are given at the freezing point of water and 1 atmosphere of pressure, in both cases here. Air is way less dense than water. Water is 1,000, air is 1.29, okay? Or in pounds per cubic feet, 0.081. Ammonia, even less dense, okay? Carbon dioxide, a little denser than regular air. Still way less than water, though. Carbon monoxide is down here not as dense as carbon dioxide and a little bit less dense than air. Now, okay, I think someone's microphone's on and you don't realize it. Okay. All right. Let me say this about this one. Carbon monoxide. Remember, that's poisonous. It's deadly. Carbon dioxide is also deadly if you're breathing straight that, but carbon monoxide is deadly for a different reason, and it's very deadly. If you are in a closed environment that you think carbon monoxide may be present, it's good to get down on the floor because the oxygen is going to be near the floor, carbon monoxide is going to be nearer the surface, is going to be higher up. So that's why if you think carbon monoxide is present and you're trying to get out of a place and don't want to breathe too much of it, get as close to the floor and crawl out of the place as possible. Most of the time, just don't put yourself in that situation. Helium is the second lightest of all gases, and look how low its density is. 0.011 pounds per cubic feet, or 0.178 kilograms per cubic foot. Hydrogen is the very lightest of gases. We're going to have to wait until this block gets out of the way. It's going to fade out in a minute. And you'll see the other ones here. You'll see hydrogen, then nitrogen, the oxygen, and then propane. Propane is going to be up here more in the, okay, here, let's get them while we can. Hydrogen, the very lightest, lowest density. Nitrogen is pretty low, okay, but oxygen 1.43. So you see it's considerably denser than carbon monoxide and not quite as dense as carbon dioxide, but denser than carbon monoxide. So if you're in that situation that you think carbon monoxide is present, get low. Crawl out of that space, okay? You don't want to be breathing the carbon monoxide. The oxygen's going to be further down. Propane is a little bit denser than oxygen, and propane is sort of like natural gas. Natural gas may not be exactly propane, but it's very similar. Oh, let's see. Somebody's trying to come in. I think it must be, I can't see. Mika. Oh, Mika must have had to go out and come back in. Okay. So Mika's coming back. So we've still got, yeah, 6 students plus me. So here's your table of densities. And that's the last table, the last slide in the book. So let's go to example 1, which will be, now I don't have my watch on, my battery needed a recharge, so I've got it recharging right now. So y'all have to help me keep up with time. I'll keep on talking all night long, so if you want to leave, be sure you keep up with time and let me know. All right, so let's go to example 1. So we'll go back to the whiteboard. Okay, and I think I'll go on and clear that drawing off. Okay. Now, I heard Jalen cast his vote. What do the rest of you think? Do you prefer my writing with my fingertip, my right fingertip, or using the stylus? Do you have a preference? Nobody's saying anything. Okay. I'm going to use the stylus then if y'all don't object. Find the weight density. Okay, the weight density is D sub W. That's what we're looking for. Someone remind me what the formula for weight density is. Anyone remember? It was so long ago, maybe 10 or 15 minutes. The force due to weight. Yeah, and that's what this does. If it won't draw, F sub W divided by volume. So find the weight density of a block of wood. Now this is what we know about the block of wood. The block of wood is 3.00. Now that's the other thing this does sometime. I put the decimal there, I went to draw my 0, my pen was off the page, and yet it connected the decimal with the top of the 0. I don't know why it does that. So that's 3.00 inches by 4.00 inches, and sometimes the slashes work and sometimes they don't. Okay, and sometimes the I is right and sometimes they don't. By 5 inches. It's a very precisely cut piece of wood. 5.0 to the nearest hundredth of an inch. Every dimension. Very precise. And there it went and did it again. Okay. There's the I and here's the N. Okay. There are your dimensions of your piece of wood. Okay. And it gives the weight, which is F sub W. Okay. That's too many wiggles in the W, of 0.0700 pounds. 0.7700 pounds. Okay, there's the weight. Now, we've got a problem, don't we, Houston? We don't know the volume, but we have the dimensions. And this is a rectangular piece of wood. They show it in the picture. That stands for length, width, and height, or depth, or whatever you want to call it. But it's given in inches, not in feet. So here's a couple of ways to go. I think it would be easier to calculate this in cubic inches, which means you just multiply each of these dimensions together. Okay, so let's just do that. That's going to be fairly easy to do, and that's going to be 20 times 3 is 60.0 cubic inches. Now we don't usually use cubic inches. Usually we use cubic feet. But I knew the back of the book has this for you, so I think we've turned there before. In the back of the book, along about page 688 or so, there are tables for conversions. So let me turn back one page to 686, and there's U.S. weights and measure. They just give some of those. Conversion tables for length. We could have done it there if we wanted to, get our inches into feet. We could have done that. Then conversion table for area. That wouldn't be useful here. But then on the top of page 687, there's a conversion table for volume. That's the one we want to use. And here it says, there's a conversion. 1 cubic foot is 1,728 cubic inches. So what we're going to do here is do our times just like we did before. Blank, blank. First blank for numbers, the second for units, and then and we're trying to get to cubic feet because that's what we usually measure our density in, cubic feet, not cubic inches. So you tell me which unit goes where. Always put the units in their place. We just went through this in the example we did earlier. What unit goes where? One goes on top, one goes on bottom. Cubic inches one place, cubic feet the other. You tell me what goes where. You got it. Cubic feet on top and cubic inches on the bottom. Okay? Now, that number I just read off of page 687, table 4, top of the page, right-hand side, US, 1 cubic foot, there's a 1 that goes right there, is the same as 1728 cubic inches. So the 1728, if I can get the pen here, 1728 cubic inches. So we've matched the numbers with the units. Now we're ready for calculator. Okay, so let me move my paper marker so we can go back to that if we need to. And let me find what I did with my calculator. Telephone. Okay, let me log back in. Alright, I'm right there. So 60, whatever's in numerators you multiply, whatever's in the denominators you divide. 60 divided by 1728 equal, and that is 0.0347 and then a bunch of 2's. I'm going, yuck, I hate this thing. Why it does that, I have no idea. And then 2's. I'm going to put a bar over the 2, not meaning it's significant, meaning it's a repeating number. Okay, that's what I show on my screen is 0.034722222222. Okay, that's what I mean by repeating number. Okay, not significance. That's a different meaning for the overstrike. Okay, so there's our volume. I didn't write that down, did I? So let me write that down. This is the volume. Volume is length times width times height. We've got our force due to weight, and now we've got the volume. So we're going to take this and do 0.700 pounds and divide that by 0.0347222222222, and that would be cubic feet. Alright, so let's get our handy dandy calculator. Now what I'm going to do, since I have that on my screen, I'm going to turn my calculator sideways so I can use that 1 over x key because that's in the denominator now, and then multiply that by your 0.7. I'm just lazy that way. And that gave me 20.16. Okay? Now because that's my final answer, I need to round that. 20.16, and that would be pounds per cubic foot, okay, which would round to 1, 2, 3 digits. Look to the right, that's a 6, that's more than 5, so that should be 20, yuck, it'll go away in a second, 20.2 pounds per cubic foot. Okay, let's see how the book did. Oh, look at that. They got it right. 20.2 pounds per cubic feet. Does that make sense? Were you aware of what the formula or equation for a volume is? Length times width times height. Yeah. No, it's pounds per cubic feet. Same units. Okay, now I realize I have left something off. That's supposed to have another equal sign there. Okay. Yeah, that was what I got on my calculator screen, but that was too many digits. So what I do is I count from the first digit that you see, 1, 2, 3 digits. That's all I have. I look to the right. That's a 6. That's greater than 5. So I round the 2 up to a 1 up to a 2. So that gave us 20.2 pounds per cubic feet. Both of those answers in my mind are acceptable. It's just that the 20.2 is the correct number of significant digits. 20.16 is not. Okay, that's too many digits because all you had coming in were 3 digits here, 3 digits there, 3 digits there, and 3 digits there. That 0 up here is not significant. Those are. So you had 3 everywhere, so you can't get more precision out of a problem than you put into the problem. You only had 3 digits of precision coming in 4 different locations, so you can't get 4 digits going out. You have to round that to 3 digits, 20.2. Okay? Did that answer your question? Or did it make it worse? Now, notice here, okay, good. Notice here, we had 4 significant digits there. It's okay in the intermediate to have more digits. That's fine. You don't have to round. In fact, I would never round in the middle. That's why I actually carried all those digits here. Because, if I can find my pen, there it is. Because there's nothing wrong with carrying extra digits in the middle. It's only at the end you want to round to significant digits. It would be like if I wanted to give someone, okay, my wife and I worked this past weekend on our taxes, okay, and a lot of the things we put to the nearest penny, to the nearest penny, to the nearest penny, but when we were using TurboTax, it usually rounded to the nearest dollar. So I had no problem with putting in to the nearest penny, knowing that I was getting all the significance I could out of it. If TurboTax wanted to round at the end, that's fine with me. Okay, you can always go to a less significance. You can't move it up to more significance. So anyway, that's what we did. All right, ready for example 2? So let me get my pen here and clear the drawing. Can I erase this one? Speak now or forever hold your peace. Okay, it's going. Okay, it went. Example 2. Find the mass density. So this time we're looking for mass density, D sub m, which probably means we're dealing with the metric system. What is the formula for mass density? It's mass per unit volume, not weight per unit volume. Okay? So, find the mass density of a ball bearing, with a mass of, so they give you the mass. The mass of this ball bearing is, ball bearings are usually pretty small, so that's a pretty small mass, 22.0 grams. Now that's a very small amount of mass. 1 gram is about the mass of an aspirin tablet. So this would be about 22 aspirin tablets. That's not very massive. Of course, ball bearings are smaller than aspirin tablets, but aspirin tablets are not very dense. Ball bearings are. Okay? It's 22 grams and a radius. Okay? So let me find my pen here. The radius here is equal to, and again they give radius. I don't know why the second part of an equal sign just doesn't come through well. 0.875 centimeters. 0.875 centimeters. Now, does anyone notice anything special about the problem right now? Okay. Well, the units aren't right. Not for what they usually do. But if you recall, I said I usually like to do mass density in grams per cubic centimeter rather than kilograms per cubic meter. Okay? So if it's okay with you, let's do them in the units they gave it to us. At the end, we're going to have to go back and convert it to kilograms per cubic meter, I bet. Yes, we are. But at least for now, we can deal with them this way. Okay? Or we can go on and change now. It's up to you. I don't care. You want to change your mass to kilograms and your radius to meters, or you want to work the problem the way it is and we'll change at the end. You decide. Anybody? Change it now. Okay, we'll do that. Okay, so we're going to have to multiply this by blank blank to equal blank kilograms. Now, can anyone go on and tell me what that is without going through the conversion, or would you rather go through the conversion? I don't care which way you want to go. Convert, okay. Now, what unit go? Say again? Okay, a kilo means 1,000, which means you're going to move your decimal because the kilogram is bigger than the gram, so you got to make the number smaller. So this is going to be divide by 1,000. There's 1, 2, 3 places, so this is going to be 0.022 kilograms. Now, I think Jalen said he wanted to see it. Well, we do exactly like we've done before. Put grams on the bottom, kilograms on top, and that's what you're going to tell me to do, weren't you, Jalen? I know you were. Okay, and that would be dividing by 1,000, which is exactly what I believe it was Macy saying, or Manasseh, I can't remember who said it. Okay, is 1 kilogram, because 1,000 means kilo. Kilograms is 1,000 grams. So that means you divide the 22 by 1,000, and that's 0.022. Okay, so any way you do it, that's what it is. Now let's do the same thing for centimeters. Now I don't have enough room here, so I'm going to put my blank blank down here is equal to, and we're trying to get this to meters. So which unit goes where? Or can someone tell me how to do that? Whichever way you want to do it. You can tell me the answer, you can tell me how to get the answer. What unit goes where? One's on top, one's on bottom. 1 centimeters, 1 meters. Which goes where? Yep, centimeters on the bottom and meters on the top. Now, how many centimeters in a meter? How many meters in a centimeter? Thinks how many cents in a dollar? Do you know? Sure you do. 100. Centi means 100. Think a century is 100 years. Okay, it's 100 centimeters is 1 meter. Okay, so that means you're going to divide this number by 100, meaning you're going to move the decimal 2 more places to the left. So that's going to be 0.00875. That's how many meters it is. Okay, now that's a radius. Remember, radius. What is the shape of a ball bearing? Does anyone know? Please say yes. What's the shape of a basketball? Say again? Okay, what's the shape of a ball bearing? What's the shape of a... Oh, it did. Huh. What is the shape of a ball bearing? Okay, circular would be the area, you might say, but the volume would be a sphere. Not a circle, a sphere. Yeah, the shape is circular. That's a cross-section of it. But the volume is a sphere. Okay? Now, if you go back to the back cover of your book, and remember I almost showed you the wrong thing before because I was looking at it upside down. There was a circle that's two-dimensional. The sphere is three-dimensional. There's its volume. What is its volume? Can you read it? 4/3 pi r cubed. That's the volume of a sphere. 4/3 pi r cubed. Okay? So, we need the radius, but we have to have it to get volume, but the volume oops, I can't write on the screen there. Duh. Okay. The volume is, that formula we just did, 4/3 pi times r cubed. Okay? Which is going to be 4/3 times pi. We're going to leave pi alone for now. And then the radius is this number here. Now, do you prefer scientific notation or do you want to leave it just like that? I don't really care. It's a little bit easier to write in scientific notation. Which you want to do? Leave it just like that or put it in scientific notation? Okay, so that would be 8.75 times 10 to the, now how many places did you move that decimal? 1, 2, 3. Times 3, not times 3, times 10 to the third. The old gray cells are going to sleep on me here. I can't get my eraser. There it is. Okay, there it is. Okay. Go back to my draw mode. Okay. Times 10 to the minus 3, because that's a small number smaller than 1, so its exponent is negative. 10 to the minus 3 meters. That's what your radius is. But you're cubing that. Okay? So, let's get your calculator and let's step through it probably together. Okay? And I'm going to turn it sideways so we can use the scientific mode here. Okay, we can start with the 4 divided by 3. So 4 divided by 3 times pi, well, there are pi keys on here. By the way, it's 3.14159, blah, 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 blah. Okay, times, okay, now we've got to enter our radius. Okay, and again, I think it's a good idea to open a parentheses here, and you'll do 8.75 EE or EXP if that's on your calculator, and then you do the, in my calculator I do a 3 plus minus, okay, minus 3, close parentheses, and there's your 0.00875 just like we had, cubed. So now we're raising that to the third power, and there is an x cubed thing on my calculator right there, I believe it is. So I'll press the cubic key. Whoa, and that makes a pretty small number. Did I hit equal? Okay, then when you hit equal, you still have a very small number. So let's see if I can write down that number. I'm going to write it in scientific notation. Okay, that's equal to, my first non-zero digit is 2.8, and you could round it to 1 there. I don't want to. I'm going to keep a few more digits. 80617 6. You don't need this many, but I'm just writing them being stubborn. 2. I'm going to leave it at 2. Okay, that's the numerical part. Now what's the exponential part? How many places did you need to move that decimal? 1, 2, 3, 4, 5 zeros and one more for the 2, so it's 10 to the minus 6 times 10 to the minus 6, and that would be meters cubed. All right, very, very small volume in cubic meters. But a ball bearing's a little bitty thing, you know. It takes a whole lot of them to make a cubic meter, a whole lot. But now we've got everything we need to come back up and enter our formula here. The mass we calculated was 0.022 kilograms. That's a pretty ugly K. Divided by this number here, 2.80. You don't have to carry that many digits if you want to. I just decided I'd do it. 0.6162 on the intermediate. You don't carry that many at the end, times 10 to the minus 6, and that would be meters cubed. That's a pretty ugly M. Okay, cubic meters. But the thing is, I don't have to enter those numbers because, again, that number I have there is your denominator. So since I want it in the denominator, I'll put 1 over x key, and that makes an incredibly large number. Okay, and then I'm going to multiply that by the 0.022 and hit equal, and that gives me, yeah. Now, I'm off 1 decimal, I think, from what they are, but I think we can live with it. Okay. That gave me a number that's 7,800, and it says 39.8. But since this is my final answer, I'm going to round that 3 to a 4. Ooh, that's going to go away in a minute. I said a 4 and it only wrote a 1. 7,840. Yuck, it did it again. Okay, 40. Okay, and that would be kilograms per cubic meter. So 7,840 kilograms per cubic meter. I had 7,839.8889 blah blah blah. But you only have 3 significant digits, so count 3 digits, 783, look to the right, the 9's greater than 5, round the 3 up to a 4, and then I put a 0 instead of the 9. So 7,840 kilograms per cubic meter. Okay, now just for funsies here, let's go back momentarily to our table here. Remember, 7840. So let's go back to our sharing here. Go back to the PowerPoint. 7,840. Look at that. I bet you that ball bearing is very close to being solid iron. Not exactly. It's a little denser, so it probably has some other things in it, like maybe chromium or something else to keep it from rusting. Okay, like making stainless steel. Okay, so it's probably an iron-based ball bearing, which most of our ball bearings are. It's some type of steel, not iron, but steel, and that makes sense. So and now in the book they had 7,830. The reason that I came out another digit from them is they rounded early. I like to keep the digits for a long time before you round. Okay, so that was example 2. Someone let me know. Well, let's see, my phone has a clock on it. Yeah, I think we have time for example 3. So let's do example 3. Any questions on 2 before we leave it? There was our answer. They got 7,830. We got 7,840. Usually if you're within that last digit or two, you're okay. Okay. They must have come up with a 7,834 or something like that. We came out with a 7,839. So it's just because I carried more digits here than they did. They rounded here, and of course that made they rounded up here, and that took them down here. So I think our number is more precise. Okay. All right, to erase. Okay. So let's do example 3, bottom of page 331. Find the weight density of a gallon of water weighing 4.34 pounds. So what we have here, let me get my Wacom in place. What we have here is a gallon of water. Now a gallon is a capacity measurement. It's not a volume measurement. Okay? But it can be related to a volume. So we're going to do a blank blank to get us into, and since we're dealing in pounds, we want this in cubic feet. That's the volume we're going to get to. Gallons is in a sense sort of like a volume, but you call it a capacity. So we're going to do a conversion there. Okay? Now, it says it weighs 8.34 pounds. So 8.34 pounds is going to be the weight. That's F sub W. Now this answer we get here, whatever that is, that's going to be our volume measurement. What is weight density? D sub W. That's what they're asking for, right? Right is the weight density, and that is simply force, weight, per unit volume. So the big problem here is to get the gallons into cubic feet. What unit you think is going to go where? Y'all are getting good at this. What unit goes where? Gallon goes on the bottom, you're absolutely right, and cubic feet goes on top. Okay, and again, head to your tables in the back of the book. And remember, we had the conversion table for volume was on page 687, and let's see if we can find. There it says 1 U.S. fluid gallon is equal to 4 U.S. fluid quarts. We knew that. 8 U.S. pints. We knew that. You probably or may have known 128 U.S. fluid ounces. Okay, so what? Or 231 cubic inches. But finally we get to 0.134 cubic feet. So this is 0.134, I believe it was, wasn't it? Yeah. 134 cubic feet. The decimal's right there. And that would be 1 U.S. gallon. You see that in the table? It's the next to the last line in table 4 when you're converting. Now, there is actually another one we could have used, and that would be 1 cubic foot is 7.47 gallons. We could have done it that way, put 1 cubic foot on top and 7.47 gallons on the bottom. That might have given us a little more precision. Don't know for sure. What they do, they get it to cubic inches, and then they have to convert that to cubic feet. That seems like to me they're going around their ear to get to their nose. So I found that sort of an awkward way to do it. So let's do it this way. So we'll take 1 gallon and multiply it by here. I was trying to move. Come on, where are you? There you are. Okay. Here the gallons go out. And of course, if you multiply 1 gallon by 0.134, that gives you 0.134 cubic feet, because 1 gallon is that much. So now that's what you put down here, 8.34 pounds divided by 0.134 cubic feet. Now, the problem is they told us it was water. We know what the answer should be, but let's see what we get. I've done it before, and I almost guarantee you it's going to come off a little bit, but not too much. Okay, pull up the calculator. 8.34 divided by 0.134. 3 digits everywhere, and that gives us 62.9. 62.9 pounds per cubic foot. Now we know that doesn't sound right, does it? Because water is supposed to be 62.4 pounds per cubic foot. Now, their calculation, doing it the way they did with pounds and inches, they did 2 conversions with it. They came out exactly 62.4, rounded to 62.4. Again, your conversion was right what they had in the back of the book, so you're stuck with it. So it's fine. That's going to be close enough. 62.9 versus 62.4. Don't sweat it if you don't come out exactly right, as long as you're close. That's good. Close counts in horseshoes, hand grenades, and hydrogen bombs. No, we won't go into that. Okay. You don't have to be all that precise. So that was example 3. And unfortunately, that takes us right out of time, doesn't it? Y'all were supposed to remind me, and I reminded you. Now, part of the reason for that is I'm so hungry I wasn't about to forget it. But I need to find my eraser. There it is. Okay, and erase some stray marks on the page here, and some that are not so stray. Alright, so we'll begin next time with example 4. I wish we had gotten a little more progress made today, but there were some questions at the beginning and in the between, so I'm glad to answer the questions. Okay, we've still got to do example 4, 5, 6, 7, 8, and 9. I think we can do those next time. Then they have a little bit more at the end of the chapter, but not much. So your problem set here, I think you can do any of the odds 1 through 7. And I think you can probably do 9, 11, 13. You may hold off on 13. We'll do one like 13 next time. So go through 11. Any of the odds 1 through 11. Okay? Any questions? All right. If no questions, I'm going to stop sharing now. I'm tired of sharing. Okay? Any issues before we go? Oh, I'm trying to advance with my finger on my Wacom and it won't do. Okay, so I'm going to stop the sharing and we'll end the session unless you have questions. Were there any last minute questions? No. All right. Have a good couple of days. We'll see you again on Thursday. Okay? All right. Good deal. Bye-bye.